So we are very close now to having finished the proof of the prerequisite theorem. Let's just finish this off. So at present we've got to this inequality here. We know that the difference between the upper and lower sums for the product function is less than or equal to this bound for the function f times the difference between the upper and lower sums for the individual function g plus the bound for the function g times the difference between the upper and lower sums for the individual function f. And of course, because we know the function f and g are both Riemann integrable over the interval ab, we know that for clever choices of dissection, we can make these differences here as small as we like. So we want to use that fact to show that we can make the difference between the upper and lower sums for the product function as small as we like through a clever choice of dissection. So let's take an epsilon greater than 0 and let's find a dissection d such that this difference is going to be less than epsilon. So what we can now do is apply the Riemann integrability criterion for the function g and the function f. So I know that there will exist a dissection which I'll call d1 of the interval ab such that the difference between the upper and lower sums for the function g using that dissection d is less than, and I'm not going to use directly epsilon, instead I'm going to use epsilon divided by 2 times bf. Of course, the reason the bf needs to be there is because I want it to cancel with this bf here. And the reason the 2 needs to be there is I'm going to get an epsilon over 2 from this and an epsilon over 2 from this, so overall the sum will be less than epsilon. So 2 is just a constant, bf is a positive constant, so we're dividing through by a positive constant here. So we take our epsilon, which might be very small, divide it by a positive number, that just makes it even smaller. But we know the Riemann integrability criterion can do however small you like, so there will exist a dissection d1 such that this difference is less than that value. Similarly, we can apply the Riemann integrability criterion for the function f, and we can find a dissection d2, so these two dissections might not be the same. In fact, they're very unlikely to be the same. They could be the same, but they're very unlikely to be the same. But you can find a dissection, unless you were trying to make them the same, but you can find a dissection d2 such that the difference between the upper and lower sums for the function f is less than, and this time we've got epsilon over 2 times bg again because we want the bg to cancel, and then we'll have epsilon over 2 from here and epsilon over 2 from here. So again, bg is positive, 2 is certainly positive, so we're just dividing our epsilon by a positive number. That just makes it smaller but still a positive number, so you will be able to find, you're guaranteed by the Riemann integrability criterion to be able to find a dissection d2 such that this inequality holds true. Now, the problem is that this inequality, you have to have the same dissection everywhere for this inequality to hold true. So we can't have d1 and d2, so how are we going to get around that? Well, of course, we're going to build a common refinement of the two. So we will build a third dissection, d bar, which will be a common refinement of both d1 and d2, so it will contain all the cuts from d1 and all the cuts from d2, so it's a refinement of both of them. And because it's a refinement of both of them, I'm able to conclude the following two inequalities. So if I use d bar and construct the upper and lower sums for the function g using d bar, and then look at the difference between these two, because it's a refinement of d1, I know that this difference between the upper and lower sums for d bar is guaranteed to be less than or equal to the difference between the upper and lower sums for d1. And since this is strictly less than this value, and this one is less than or equal to this, then by transitivity I know that this is going to be strictly less than this value, epsilon over 2 times bf. And the same argument applies here. So if I create the upper Riemann sum for the function f using d bar and the lower Riemann sum for f using d bar and look at their difference, because d bar is a refinement of d2, this difference is guaranteed to be less than or equal to this difference using the less refined dissection. And since we know this one is strictly less than this, then by transitivity we know that this is strictly less than this value epsilon over 2 bg. And now I have a dissection d bar for which both of these inequalities hold true, which I can now apply up here. So if we now use this dissection d bar and create upper and lower Riemann sums for the product function fg and consider what the difference is between the two, then this inequality will hold true. So this is going to be less than or equal to this, where you put in d bars for the dissection here. But now we know these hold true for d bar, so putting this one in here we can see that this bit here is going to be less than epsilon over 2 because this is less than epsilon over 2 times bf. So multiplying it through by bf, you're then going to have that this thing is less than epsilon over 2. Similarly, we know that this bit here is less than epsilon over 2 bg, therefore bg times it is less than epsilon over 2. So adding those two things together, this one's less than epsilon over 2, this one's less than epsilon over 2, hence this overall thing is strictly less than epsilon. So by transitivity, if this is strictly less than epsilon and this is less than or equal to this, then this is strictly less than epsilon. So we now know that this difference between the upper and lower sums using this refined dissection d bar of the product function fg is strictly less than epsilon. So for any epsilon then, I have specified a way for you to build a dissection such that the difference between the upper and lower sums for this product function is less than that epsilon value, and hence it holds true for all epsilon values, hence the Riemann integrability criterion is satisfied. So we can conclude therefore that this function f times g is Riemann integrable over the interval ab if the two individual functions f and g are both Riemann integrable over that interval. So we have now finished proving that prerequisite theorem that if you have two functions that are Riemann integrable over an interval, then product them together, create a new function, and that is guaranteed to be Riemann integrable over that interval. We're now ready to prove the integration by parts formula, and this, you'll be relieved to know, is beautiful and simple. It's a simple corollary of that prerequisite theorem and the second fundamental theorem of calculus. So IBP, integration by parts. So the setup, we're going to have two functions, f and g, that are both real-valued functions defined over this interval AB. And we're going to assume that both of these functions are differentiable everywhere on that interval AB. So you'll have f prime defined as a real-valued function everywhere over that interval, and you'll have g prime defined as a real-valued function everywhere over that interval. And we're going to assume that these two derivative functions, f prime and g prime, are Riemann integrable over the interval ab. And remember, them being a derivative of another function does not immediately imply that they are Riemann integrable. There are examples of functions that are the derivative of another function over an interval, and yet they are not Riemann integrable over that interval. They're very horrible functions, variants of the topologist sine curve, but there are counterexamples, so you do need that added assumption that these two functions are Riemann integrable. Now note, the initial functions f and g are also going to be Riemann integrable over the entire interval ab, but we don't actually need to add that as a separate condition because we've already got the fact that they're differentiable everywhere on the interval ab, and differentiability implies continuity, so they're going to be continuous everywhere over their intervals, and being continuous everywhere over your interval implies that you are Riemann integrable over that interval. So we know that f and g are Riemann integrable. We don't need that as an additional assumption. We get that for free from the fact that they're differentiable everywhere, but we do need the initial assumption added on that these two derivative functions are Riemann integrable. Now what we do is we consider the product function of f times g, which of course is a real-valued function over the interval ab. Now, by the product rule, because both f and g are differentiable everywhere over the interval ab, then this product function is also going to be differentiable everywhere over the interval ab, and the value of its derivative anywhere will be given by the product rule, so it will be f prime at x, so x is some point in this interval. The derivative of this function at that point will be f prime evaluated at x times g of x plus f evaluated at x times g prime evaluated at x. Now this function that is the derivative of the product function, it's going to be defined over the interval ab and it's going to be a real valued function. This function is going to be Riemann integrable over that interval. The reason being is that look at what it's built out of. We know all of these things are Riemann integrable over the interval ab, so we assumed f prime and g prime were Riemann integrable over the interval ab, and we got that f and g were Riemann integrable by the fact that they were differentiable everywhere and therefore continuous everywhere. So now what we've got here, this is the product of two Riemann integrable functions, this is the product of two Riemann integrable functions, so these bits are Riemann integrable, and then you're just summing two things together, and we know linearity holds true, so the sum of these two Riemann integrable functions will also be Riemann integrable, Hence, the overall thing is guaranteed to be Riemann integrable over the interval AB. And further by linearity, the value of the integral of this function, the derivative of the product function, integrated from a to b, dx, will be equal to the value of this bit integrated over AB plus the value of this bit integrated over AB. So it will be equal to the integral from a to b of f prime g dx plus the integral from a to b of f times g prime dx. Now what we can do is we can apply the second fundamental theorem of calculus to this side, because this function that we're integrating here, we know it's going to be Riemann integrable over that interval, but we also know that it is the derivative of another function that's defined on that interval, this function, the product function. So by the second fundamental theorem of calculus, the value of that integral is going to be the value of this function evaluated at the upper bound minus the value of this function evaluated at the lower bound. So the value of this function evaluated at the upper bound is f times g of b, which is f of b times g of b, and the value of the function at the lower bound is f times g of a, which is f of a times g of a. So the value of this integral by the second fundamental theorem of calculus is this. Now note, the second fundamental theorem of calculus cannot tell us that this is Riemann integrable, but we've already managed to conclude that it's Riemann integrable by our prerequisite theorem that the product of two Riemann integrable functions is Riemann integrable, and by linearity that the sum of two Riemann integrable functions is Riemann integrable. The second fundamental theorem of calculus then tells us if the Riemann integral exists of your derivative, then the value of it must be the value of the antiderivative evaluated at the upper bound minus the value of the antiderivative evaluated at the lower bound, which is exactly what we've applied here. So we know that this is equal to this. We're replacing this with this now, and it's going to be equal to this. What we need to finally do to get the integration by parts formula is just take this bit to the other side, so subtract it off from both sides, and we'll now write it in terms of this. So we've got the integral from a to b of f prime g dx, which is that bit, is equal to this bit here, so f of b g of b minus f of a g of a, and then minus this bit from over here, so the integral from a to b of f g prime dx, which is the integration by parts formula. So there you have it. I've put it in a box. We have proven the integration by parts formula for Riemann integration. We'll finish there. Thank you for watching.